Welcome back. In this lecture, we will briefly discuss hierarchical clustering. Here is our lesson objective. So, sometimes we want to find groupings in data that also allows us to have a hierarchy, and we may want to have clusters that can be contained within other clusters. And doing this is what's called hierarchical clustering, and kind of a key aspect of this is what's called a dendrogram, and this is a visualization that shows the result of hierarchical clustering that communicates both the clusters and their relationship to each other. So here what I drew is on this line is just kind of a list of the samples. This is not a feature space or anything. This is just some arbitrary ordering of samples. And sort of this first grouping of them, specified by those brackets that are on their side, these are an initial clustering. So we have 6 different clusters. 2 of the clusters are inhabited by singletons. Now what we can do is we can look to cluster those clusters, and there turns out to be, 3 clusters. So 3 groups of things that go together. Now notice we have members within a cluster that are themselves clusters. And then we can go up further layers. If we would go up one more layer, we would be at a root and everything would be in a group. So there's no point in doing that except for identifying convergence. But this is an example of a dendrogram. And what I described is an example of a run of something called agglomerative clustering. And here's some cluster labels as well. So agglomerative, also called bottom-up, this builds the dendrogram from the samples going upward. And the stopping criteria is very straightforward. It's when all clusters are merged into a root. So we knew we stopped there in that previous example when we only had 2 clusters left. The second type is called divisive or top-down, and this starts from all the data and then recursively divides it up into smaller clusters. And the stopping criteria is when each cluster has a single element. Now, agglomerative is what has become much more popular, and there's more efficient implementations for it as well. So linking methods. So how do we link 2 clusters together? So there's a couple different ways of doing this. One is single link, where which is the distance between the closest points in the cluster. The other is called complete link, which is distance between the furthest points. And we also have things like average link and centroid based, which are kind of a compromise between single and complete link. The issue with the single link is it causes what is known as chaining, where you could have a cluster that kind of spans out further and further because you're iteratively adding elements to that cluster. And so the reason why we still see single link in many implementations is because it ends up being something that runs very efficiently. But in general, we're going to see quadratic runtimes or something like n squared log n runtimes even, especially when you get to things like average link. So anyway, this concludes our introduction to hierarchical clustering. Stay tuned for more content.